So, a very good morning to all of you. Let me thank the organizers for inviting me over. I would like to present a part of the recent work that we have been doing. This is regarding multiple timescale phenomena on complex networks. Let me quickly introduce the stage for this. So, we address complex systems in very different ways. One way to look at it is from the complexity of the intrinsic dynamics of its component units. The other way is there can be complexity and heterogeneity in the way they are connected. The third one that we are now interested is how difference in dynamical timescales of each individual system can affect the pattern of can affect the emergent dynamics of the system, especially when there is a heterogeneous pattern in the interaction. So we use the framework of complex networks and study what happens to systems when they are interacting on a complex network but with different dynamical timescales. So there are different systems where this is applicable. One or two I am showing, some of them I am showing here. One is on the electrical activity of neurons, then chemical reactions. So these are all things that can happen at different timescales. We have in fact applied it to this last one, climate systems, where the convections in that ocean is much slower than the convections in the atmosphere. Similarly, in the context of neurons, how the difference in the timescales can affect and give rise to different patterns in the behavior of the neurons. So some of our interesting results are, we find that there is suppression and recovery of oscillations. There is synchronization, basically frequency synchronization, and there is a self-organization of the whole system that is possible. And in the last context of neurons, we find frequency-locked clusters and traveling sequences are possible on the whole network. So with that, let me start with a system of Rossler systems. And we consider Rossler systems in the periodic regime by choosing the parameters, and we combine them on a random network to begin with. And then we are choosing the dynamical timescales of each individual system as tau I here, which means whatever change is there in the dynamical timescale is taken over to this side and added as a parameter tau I, which means tau I less than 1 makes the system slower. So to begin with, we are considering the whole network having two timescales. One is where tau is equal to 1, which is the normal time scale, and there are a set of systems, let us say m number of systems, which have a time scale which is less than 1. So a system of interacting systems with time scales, two time scales, one is slow compared to the other. And we find that when that happens, it's possible that the systems will get all their oscillations suppressed and they go to a state of amplitude death. So here we show that as we change the number of slow systems, what happens to that? So to begin with, the number of slow systems are small. There is oscillatory behavior in the system, but as m increases, it goes through amplitude death. And once again, the oscillations are recovered, but at this end, when it is recovered, they are all having very slow oscillations. So this is shown here by plotting the difference in the amplitude, average difference in the amplitude of all the oscillations in the network. Now we find that when they are not going to a amplitude suppressed state or amplitude death, there is frequency synchronization in the system, which means that the slow and the fast are going like this with a phase shift as well as change in the amplitude, but their frequencies are the same. So in a parameter plane like this, which are this time scale parameter tau and the coupling strength epsilon, this region corresponds to region of amplitude death, and here we get frequency synchronization, while this is instability and this is a transient state. And another interesting thing that we find is that when there is suppression of amplitude and recovery of oscillations, etc., there is a crossover phenomenon that we observe as we change the number of slow systems. For example, to begin with, the slow systems are always having smaller amplitude compared to the fast systems. But as you increase m, there is a point where there is crossover and the slow systems becomes larger in amplitude compared to the fast system. So this is a reversal in the amplitudes of oscillations that happens as the number of slow systems in the network increases. So similarly, there is a crossover into frequency synchronization that also happens, because here we are plotting the emergent frequency when the systems are in the frequency synchronized state. The emergent frequency of all the systems, they are plotted as a function of increasing m, and this is the average frequency which is plotted here. So we find that at some value of m, the emergent frequency crosses over to a suppressed state, which means lower than the frequency of the average frequency of the whole network. And then this transition to amplitude depth can depend on the connectivity of the network, because basically we are considering here a random network. The connectivity depends on the probability P with which we are generating the network. So if P is very small, that means it's a very sparse network, and if P is large means it's highly connected network. And we try to see how this transition to amplitude depth depends on the connectivity of the network. Is there a minimal P which is required so that amplitude depth can happen in the system? And we find that by plotting the fraction of realizations, because we consider a large number of realizations, and the fraction of realizations that go to amplitude depth is plotted as a function of P. So in a way, this represents the probability of transition to amplitude depth. And we find that depending upon the value of M, there is always a particular value at which the transition to the amplitude depth happens for the all the number of realizations. We take Pt to be the value at which this transition or the fraction becomes 0.5. And then by dividing it like this, P minus Pt by delta, where delta is the width of this transition curve, we find all these can be crunched into a single curve where we have all of them corresponding to different values of M. And then there is a scaling in this transition which depends on the size of the network. Here we are plotting the same transition, but with respect to size of the network, with respect to P for different sizes of the network. Once again, this transition curve is shown here, and here we find that the transition follows a scaling relation like this, where Pc is the critical transition, and this follows an exponent or scaling index alpha here, and which changes with n. So if you plot it as a function of 1 by n here, we find that with error bar we can put them on a scale, on a straight line like this, and in the limit 1 by n tending to 0, which means in the large n limit of the size of the network, they would give a value of index alpha which is approximately equal to 2 by 3 here. Now I move on to scale-free networks, the same type of dynamics on a scale-free network. But we find that we address a slightly different question here. Whatever amplitude depth, recovery, everything happens in this context also. But here I would like to concentrate on a slightly different thing, that we ask the question that suppose initially all systems have the same time scale and they are all synchronized, and then due to some reason, either by a control from outside or due to some defect in the one of the systems, etc., one of them goes slow. So how the slowness of a single system in the network affects the dynamics of the whole network. Of course, they will move out of synchrony. So onset of desynchronization is something which is immediate, but the time taken for that will depend upon the connectivity of the network. It will also depend upon the shortest path of every node from that particular slow node, as well as the degree of the other nodes. So these are all characterized here in this slide. So the time taken to move out of synchrony is characterized by calculating the variance about the mean here, and then we can see that the number of systems that move away from synchrony in a given range of time is plotted here. Similarly, the time taken to move away from synchrony versus the degree. So this is the degree of the slow node. So depending upon, if you make a hub a slow node, then immediately the slowness spreads and the time taken is less compared to making another node which is not a hub, like a low degree node, etc. And this can be further characterized by calculating the total time. So this we say is the spreading of slowness on the network, the time for desynchronization, which means the time taken for all the nodes in the network to move away from a state of synchrony. We find that this total time taken depends upon the degree of the slow node in this way, because one of them, which we call as the source node, is the one which is made first slow. So then if we find that it depends upon the degree of the node, and we can put a smooth curve like this which follows as A by K plus B, where it is inversely depending on the degree of the slow node. And once synchrony is lost in the network, we find that for a range of parameter values, the network will self-organize into a frequency synchronized state, and this is the self-organization time that is plotted here. And when we have multiple time scales also, we have similar results with slightly different types of scaling behavior. But I have one more result where we have applied it to a community structure network of neurons, where we have neurons which are forming different modules like this, and then they are connected by connections which are inhibitory. So within the module there is no connection, but between modules there is an inhibitory connection. So we are using an HR model of neurons, and we find that because of this, there can be traveling burst sequences that go round and round among the modules like this. So this is how we introduce the time scale parameter. 2 of them are fast while 2 are slow. And then we find that depending upon the other parameters, we can have different types of patterns of synchronization, patterns of bursts happening. So we have sort of quantified all of them here, how it happens. F1, F2, S1, S2 means the fast one, next the fast one, then 2 slow one. And these are periodic. It is again and again the same sequence is being repeated among the neurons. And we characterize them based on them, how many fast, how many slow, like that. And the range of scale, time scale parameters are shown here. And in this case also, there are frequency locked clusters that happen among the neurons. We find that even when the frequencies are changing, the locking remains the same. And initially, all of them are frequency synchronized. Then they become 2 different clusters having 2 different frequencies, but they are clusters of slow ones and fast ones, like that. So I don't have time to summarize. Let me stop at this point. And these are the references. The first part of the work is the PhD thesis of my student Kajari Gupta, who now completed in IISER Pune. And the remaining one, the last part of it, the neurons work, was done as an MS thesis by Kunal in IISER Pune. And thank you for your attention. We used the Barabasi-Albert algorithm.
Okay.
And then we
so you couldn't vary the exponent. The exponent is always 3.
Yes. We have not considered varying the exponent. Most of the results we have done it, but most of the results I showed are all for the same value of the exponent.
I see.
You mean the power law index? That's the same.
Any more questions? Tariq.
Of putting one node as a slow time scale, and suppose you make it non-identical. So you have Rossler oscillators which is identical Rossler oscillators, correct?
Yeah, you mean the parameter also, other parameters are also.
So instead of making it slow, you make it different in by another manner. Then also desynchronization will take place.
Non-identical means?
Non-identical means parameter of this Rossler oscillator that you can take different than the rest of the nodes in the network.
There are many results on that, non-identical Rossler oscillator.
So then part 2 desynchronization, so results would differ a bit if you instead of making it slow.
Along with that, time scale also mismatch is there. So that case we have not checked. We have checked for chaotic Rossler. Now we have shown the results for periodic Rossler. We have tried for chaotic Rossler also, where the parameters are different. But in our case, the difference between one oscillator and the other is in dynamical time scale alone, not in the other parameters. But other parameters makes them anyway non-identical. So mostly it goes to amplitude. Those are non-results.
Okay, so let's thank all the speakers of the session and break for coffee.